Okay, and then let me change my share. We're going to look at my doc-UCam, my recorder here, the doc-UCam. All right, so this is now example of eigenvalues, eigenvectors in section 1. Okay, so let's begin with this example. This is example, and we are in section 7.1. Okay, so for this example, suppose I have a column vector. Okay, so this is column vector 1, negative 1, 1. Okay, suppose I have that column vector. And we want to verify. Let's start by saying this. Let's verify that this column vector is an eigenvector. Is an eigenvector of some matrix. And that matrix, I'll give you the matrix. So suppose my matrix is this 3 by 3 matrix, 0, -1, -3. And then I have 2, 3, 3. And then the next one is -2, 1, 1. Okay, so suppose that's my symmetric, no, I'm sorry, not symmetric, but the square matrix of order 3. It doesn't have to be symmetric. It could be, but it doesn't have to be. Okay, now to verify that this is as an eigenvector, what we need to verify is this. Does AX equal to lambda x? That's what we need to verify, right? So for this one, again, matrix A is the matrix 0, 2, -2, -1, 3, 1, and -3, 3, 1. That's matrix A. If you multiply that by x, the column vector, and remember, x here is the matrix of variables, so that would be like x1, x2, x3, the solution to x1, x2, x3 of a system. So when you multiply this, I mean, that's easy to multiply. We're going to get -2 to -2. Okay, that's just A times X. Now, from this column matrix, I can actually factor out a -2, right? A constant -2, and this becomes 1, -1, 1, right? Therefore, we can see this now as in the form of a constant, which we call lambda, and then times x. True? Therefore, in this case, lambda is going to be -2. And lambda -2 is actually, it's called an eigenvalue. So it is an eigen value of that matrix, which makes this vector x an eigenvector of the matrix. Okay. Now, if I want to find all of the eigenvalues, by the way, this is just one of them. If I want to find the eigenvalues, all of them, and then we need to look at the determinant of this matrix, lambda I. All right, let me, my eye doesn't look impressive. Okay, so this is going to be lambda I minus A. I need to find the determinant of that matrix, right? And for this one, lambda I, remember I is a 3 by 3 identity matrix. When you multiply by lambda, the main diagonals are all going to be lambdas, right? Minus matrix A, which is this one. So you see lambdas on the diagonal of this difference between the two matrices. So it's going to be lambda 2, -2. That's 2, -2 coming from matrix A. And then -1. Then it's going to be lambda minus 3. That's lambda. Second row, second column of identity is 1 times lambda is lambda minus 3 because you're subtracting A. And then this element won't change. And then we have -3, 3, and then last one is lambda minus 1. Okay. Now this 3 by 3 determinant, I actually used Symbolab to do this. So I got lambda cubed, -4 lambda squared, -4 lambda plus 16. And this is what the characteristic polynomial, they call this the characteristic polynomial is. Okay. Now, And we're going to set this equal to 0 to solve the characteristic polynomial. And this now, I can factor this third degree polynomial in lambda. Because it has 4 terms, you probably recall from algebra, we can factor the fact that there's 4 terms. We can factor this by grouping. So the way I grouped them was the first 2, last 2. From the first group, first 2 terms, the GCF is lambda squared. So I factored lambda squared. And from the second group, the GCF of this one, I factored -4 from both of these numbers. Okay, and that gives me lambda minus 4 equal to 0. I recognize the common binomial, and therefore this factored form is lambda minus 4. Lambda squared minus 4 equals 0. And by zero factor principle, we get lambda is 4. And lambda, for this factor, lambda is going to be plus minus 2. You see one of those eigenvalues we found, and that's just directly from this equation. And there are 2 others. Those are the 2 other, the eigenvalues, which we could work, and later on I'll show you, these will result in 2 more eigenvectors that we can find. Okay, so hopefully everybody's okay with this. Now, if you have questions, please, folks, interrupt me and ask questions. It's okay. So everybody's good on this example, I hope. So we're done with that. That's just verifying it. And I showed you how to find the eigenvalues, but not the eigenvectors yet. Our next example, let's say now I want to find, this time, we want to find the eigenvectors. Okay, eigenvectors of this matrix. This is a different matrix now. I made it to be 1, 6, -1, 2, -1, just random numbers, folks. 1, 0, -1, random integers. Now remember, let's say for matrix A, this is like the matrix of coefficients to some system of 3 equations, 3 unknowns. So in other words, the numbers that you see in each column, these are coefficient on, would be x, y, z, or x sub 1, x sub 2, x sub 3, equal to whatever, equal to maybe 0 for a homogeneous system, and equal to something else for a non-homogeneous system. So we want to find eigenvectors of the matrix, though, okay, of this matrix. So what I'm going to do is now, to find the eigenvectors, we need to find the characteristic equations. Okay, and for this, we're going to do, because we're finding the determinant, we can do a minus lambda I, for instance. Okay, so for this one, a minus lambda I is going to be 1 minus lambda. -1 minus lambda. I'm doing the diagonals first and then bring in the other numbers. Okay, and A, the other elements of matrix A, the off diagonals, 2, 1. And then I have -1 is here, 0 below this one, 6, second row, first column, third row, first column, third row, second column. There we have that one. And the determinant of this is going to be negative lambda cubed minus lambda squared plus 12 lambda equals 0. Now, you may wonder, you say, well, why did you do, well, here I did lambda I, the one above, we did lambda I minus A, right? And in here I did A minus lambda I. It doesn't matter really how you do this. Either way, it works. And the reason is this. If I do lambda I minus A, okay, which may be what the book does. If I do lambda I minus A, this equation, these signs will be plus, plus, minus. But then this equation set equal to 0, the solutions are not going to change. I can turn around, multiply everything by negative on both sides. And then I get positive, positive, negative. That's when you do lambda I minus A. So it really doesn't matter, folks. Either way, it would work. Now, this time, from this equation now, this is the characteristic polynomial. Okay, I'm going to factor negative lambda. See, if this was lambda I minus a, I would have plus, plus, minus, and I only factored lambda. I went ahead and factored negative lambda. And that's why it doesn't really matter. You'll see it in the next step also. Whether I set negative lambda equals 0 or lambda equals 0, it doesn't matter, because from that, I get lambda 1 equals 0, right? Again, there you go. This negative lambda 0 or lambda 0 makes absolutely no difference. So lambda 1 is 0. And in here, lambda 2 turns out to be negative 4, and lambda 3 turns out to be 3. And those are the eigenvalues. Okay. So now the next step, we want to find eigenvectors, right? So let's see how we're going to find the eigenvectors. For this one, we're going to let lambda 1 be 0. Lambda 1 0 in the a minus lambda I in that equation. So when lambda 1 is 0, you get 1, 2, 1, 6, negative 1, 0, negative 1, negative 2, negative 1, which is a itself, isn't it? That's all we get. So we get this one exactly. Oops, sorry. That's I copied the wrong number there. This is going to be negative 1, correct? And the second column is 2, negative 1, negative 2, 1, 0, negative 1. I just copied matrix A here. Now, for this one, we actually need to solve the homogeneous system. Okay. To solve the homogeneous system, that means you solve the system, set it equal to 0. And then we can go through elementary row operations. This one, let's see, for example, if I do negative 6 times row 1 plus row 2, and then simply add row 1 plus row 3. So this, okay, or use Symbolab. I actually did not use Symbolab on this one. I don't know why. I went through the elimination, but let me give you the final. And in the interest of time, I don't want to waste your time showing you how to do this, because we're going to use software anyway. So this is the end result using Gauss-Jordan. I get 1, 0, 0, 0, 1, 0, and then this number is 1/13, 0, 6/13, 0, and I have an entire row of zeros. That would be the third row. Okay, so this tells me, because I have a row of zeros here, so the solution is going to be parametric solution, right? In other words, I'm going to have infinite eigenvectors corresponding to this matrix. Infinite eigenvectors. Okay, so let's see. To make this parametric, I'm going to let x sub 3 be t. Remember, these are the coefficient on x1, x2, x3. So from the second row, this is my free variable. I'm going to let x sub 3 be t. And once that is determined, then x sub 2 moves 6/13 to the other side, becomes negative 6/13, right? So that's negative 6/13 t. And then once we have that one, the first variable, x sub 1, is going to be what? Move 1/13 to the other side, becomes negative 1/13 x sub 3, which is t. So then what is this thing going to look like? Then I'm going to write my x as, factor the t out, x1, x2, x3, and put them in order. Factor the t out, so I get negative 1/13. X sub 2 is negative 6/13, and x sub 3 is 1. And there you go. So this would be when t is 1, non-zero vector, because we don't want the trivial solution again here. So non-zero. When t is 1, you get one eigenvector. Again, there are infinitely many eigenvectors that we can find, right? So that's what this is. And there you have it. The question was find the eigenvectors. So corresponding to lambda 1, we have this eigenvector. Okay. Now, this I'm going to call it x sub 1. This is my first eigenvector, which there's infinitely many of those. Okay. Now, and this tells us again, a non-zero constant multiple of an eigenvector is also an eigenvector. Now, having done this, let's, and again, if you have questions, please stop and ask questions. So there you have. Hopefully everybody's okay with this one. Now let's try the other characteristic, what you call it, eigenvalues into that characteristic equation, or into actually to our matrix. So now I'm trying lambda 2, which is -4. Okay, we're going to try that one. And what are we doing? We're solving this system. A minus lambda I equals 0, the homogeneous system. And lambda is -4, so I'm actually solving A plus 4 identity equals 0, that system. Now, A plus 4 lambda, remember, that's after you put -4 in here and subtract it. And remember, this identity matrix, I3, once you multiply by 4, it's going to have 4 on the main diagonals and 0 elsewhere, right? That's what it's going to look like. Therefore, this whole system now, it's going to become 5, 6, -1, 2, 3, -2, 1, 0, 3. And the augmented matrix, 0, 0. You go through Gauss-Jordan again with this. If you go by hand, which we don't do, let me just say GJ using symbol app. And this is what I got. I got 1, 0, 0, 0, 1, 0, and 1, -2, 0. So there's a matrix. And then from this, again, we have a row of zeros, right? So this system has infinitely many solutions. That means there are infinitely many eigenvectors for this one as well. Our free variable is going to be x sub 3. So x sub 3 is going to be t. Once we have that, x sub 2, move -2 to the other side, times 3, x sub 3 that is. So x sub 2 is going to be 2t, right? X sub 2 is 2t. And then x sub 1, move x sub 3 to the other side, becomes negative x sub 3, but then that's t. So here's our solution to the system, to the homogeneous system, that is. And I can come up with another eigenvector, which itself is made up of infinitely many. All this non-zero scalar multiple of the eigenvectors are also eigenvectors. Okay, so that would be t factored out, and I get -1, 2, 1. And there you go. So this would be corresponding to x sub 2. Okay, and that's what we got. So far, I have 2 eigenvectors, right? Let's go with lambda sub 3. Lambda sub 3, again, if you do A minus 3i, solve the homogeneous system. This time, do what I've done up here. I'm just giving you the results. It's -2, 6, -1, 2, -4, -2, 1, 0, -4, set equal to 0. Gauss-Jordan, this one. And once you resolve the Gauss-Jordan, resolve that, and you get 1, 0, 0, 0, 1, 0. And then I have 1, 3/2, 0, equal to a set of zeros. For this one, now our free variable, I'm going to let x sub 3 again. Again, notice I have a whole row of zeros. So that means our solution is going to be parametric. My free variable is x sub 3, so I'm going to let x sub 3 be t. Move 3/2 to the other side. Let's solve for x sub 2. X sub 2 is going to be negative 3/2 x sub 3, but then that's t. And x sub 1, move x sub 3 to the other side. It's going to be negative. So x sub 1 is going to be negative t. Okay. And then we can actually write x sub 3, the vector of solutions, using this eigenvector. Okay. I turned the lights on so you can see a little better. Okay, so for this one, x sub 1 is negative t, negative 3/2 times t, and then t. So we're going to factor the t out. And or actually, let's factor, how about negative 1/2? Let me do that. Instead of t, that wouldn't be wrong, but you will see why, because I like integer solutions. And so for this one, I'm going to just factor negative 1/2 t. So negative 1/2 factored from negative 1, I got to multiply t top bottom by 2, so I can factor negative 1/2. So the first element is going to be 2. Second one, half factored, negative 1/2 factored, I get 3. And out of 1, I get negative 2, and there you go. Again, t would do just as good, but I like to have integer values for my eigenvector. And there you go. This is x sub 3. So we have 3 eigenvalues corresponding to each eigenvalue. We have an eigenvector, right? Again, n distinct eigenvalues result in n. And these eigenvectors, x sub 3, x sub 2, these are linearly independent eigenvectors. Okay, so there's no correlation, no dependencies between them. And that's what these are. Now, let's see. So again, hopefully everybody's okay with this one. Are there any questions, anyone, on this one? And then we'll look at another example if there are no questions. So we are good, I hope. Okay. Now let's take a look at another example. So for this next example, we're going to see something that's slightly different than what we just did. So in this example, again, we want to find the eigenvalues and eigenvectors. Okay. This time, a smaller system. We have A equals to 3, 4, negative 1, 7. Okay. And we want to do A minus lambda I. This will give us the characteristic polynomial. So it's going to be 3 minus lambda, 4, negative 1, and 7 minus lambda, right? And then this one, once you, oops, sorry, we were looking at the determinant of this, right? We're doing the determinant. This is the determinant, right? So you do diagonals minus product of off diagonals. So when we multiply this out, we get 3 minus lambda times 7 minus lambda minus 4 times negative 1, and set it equal to 0. Okay, so our characteristic polynomial is going to be lambda squared, right? That's negative lambda lambda. It's going to be lambda squared. Negative 10 lambda, that's the OI in FOIL. Negative 3 minus 7 gives you negative 10 lambda. The last terms, the constant is 21, but then there's 4 added to it, which makes it 25. Plus 25 equals 0. And then this I can rewrite as lambda minus 5 squared equal to 0. So as a consequence, we get a repeated root, right, when we solve this. So our 2 eigen values are not distinct anymore, right? So I have an eigenvalue of lambda 1 with multiplicity of 2. So when we do A minus lambda I, solve the homogeneous system, which would be A minus 5I, this homogeneous system, we're going to get A, remember, is 3, 4, negative 1, 7, minus, it's going to be 3 minus 5 and 7 minus 5. So this will be negative 2, 4, negative 1. 7 minus 5 makes it 2. Set it equal to 0. And again, if you solve this one, this is easy to solve. You can see you multiply the second equation by negative 2 and add, you get 0, 0, 0 here, right? The bottom row becomes 0. If you want Gauss-Jordan this, and the Gauss-Jordan will give you negative 2, 4, 0, 0, 0, 0, or you can also get the other version of Gauss-Jordan because these are two dependent rows. So you can actually write this as first row, negative 1, 2, 0, and then second row, make it 0. Either way would work. So I'm going with this version. In this version, the free variable is x2, and x1 is going to be 2x2. Therefore, one eigenvector is going to be t21, correct? And if you let t equal 1, there, I'm just going to say let t equal 1, then you simply get x1 to be 2, 1. Here's my one eigenvector. Because it's a repeated root, so it doesn't make sense to do this twice, right? So another time you can let t be anything you want other than 0. Let t be 2. So here's another eigenvector. Notice 1 is a constant multiple of the other one. And that's what happens when you have a repeated root. Okay. And so there you have it. Let me see now if there's anything, something more substantial here. So all of these pretty much work the same way. I'll do another example here. Again, hopefully everybody's okay with these. If you have questions, folks, please ask. Otherwise, I really think you're okay. So let's take a look at this next example now. For this next example, we do something slightly different. So this is example. Again, we are in section 7.1 still. In this example, we want to find basis. Okay, so we want to find the basis for the eigenspace of A, matrix A, and this is A given by 0, 1, 1, and then 0, 2, 0, negative 2, 1, 3. This time, notice it's different. We want to find basis for the eigenspace of A. We haven't done eigenspace yet, so that's what we're doing. So we start with, again, the characteristic equation. So that means I'm going to do lambda I minus A. Remember, whether you do A minus lambda I minus A, doesn't make a difference. This time I'm just being different. So the main diagonal is going to be lambda minus 2 and lambda minus 3, just comparing the diagonals. And then the off diagonals won't change. I have 0, negative 2, 1, 1, 1, 0. Okay. And then we just have to find this determinant. Now this determinant, when you work this one, let me just give you the answer I got. Okay, the answer I got from Symbolab. I'm eliminating the detailed step here, folks. I got lambda cubed, negative 5 lambda squared, plus 8 lambda minus 4. We set it equal to 0. And again, for this one, you can actually factor this. The factored form of this expression will be lambda minus 1 and lambda minus 2 squared equal to 0. Okay, now this one you may ask, well, how did you get this, right? Because I didn't factor by grouping on this one. So what I did is I actually used the rational zero theorem. Remember the rational zero theorem. If P and Q are all rational factors of the constant, plus minus 2, plus minus 4, Q all all factors of the leading coefficient, in this case is just 1, then rational solutions to this equation would be in the form of P over Q, which P over Q makes it just plus minus 1, plus minus 2, plus minus 4. This is from pre-calculus, by the way. I don't know, it's probably been a while, right? That's from pre-calculus. So this is what I did. I tried 1, 2, 3, 4 like that. So I tried 1 and it worked. I tried 2, it worked, and then I got the other one. So that's how I worked it. I did not use factor by grouping on this one. So however you do it, we're going to get 3 eigenvalues of this from the characteristic equation. So lambda equal 1 from the first binomial. From the second one, lambda is going to be 2 with multiplicity of 2, right? So that means there are, because there is multiplicity, so that means, and that means this eigenvalue is not distinct. Remember, distinct means different. If you have repeated, they're the same, they're not distinct. So because they're not distinct, we're going to get 2 eigenspaces. We're going to have 2 eigenspaces of matrix A because the multiplicity is 2. Okay. Now, again, by definition, matrix X, and what is this matrix X, by the way, which is a column vector? It's a vector of variables, right? And by definition, again, this matrix X is an eigenvector of the corresponding of this is going to be an eigenvector of A corresponding to these eigenvalues. And that's going to be true if and only if X is a non-trivial solution to this equation, right? Which is what we've been doing in the previous examples. Okay, so I'm doing this now, this work with these lambdas. Therefore, if I do lambda I minus A times X, what is this going to look like? Well, it's going to look like this. It's going to be lambda minus 2, lambda minus 3, just like it is up here. 0, 0, negative 2, let's see, minus A, sorry. Minus A, so negative 2 becomes positive 2, right? So that one is going to become positive 2. So this is 0, 2, because it's negative of A. And positive 1 becomes negative 1. 1 becomes negative. This one becomes negative. 0 doesn't matter. Because again, I'm doing minus A here, negative A. And then we multiply this by x1, x2, x3 equal to the 0 vector. In other words, we're solving the homogeneous system. And we are hoping for non-trivial solutions. Okay. Now, when we work this, again, lambdas for these end up being exactly what we got up here. So lambda is going to be 1, 2, 2, right? All right. Now, we're going to try lambda equal to 2. Again, this is just a repeat of what I did up here. Okay. Now, when lambda is 2, we're going to put 2 here, 2 here, 2 here. So it's going to be 2. This one becomes 0. This becomes -1, right? So the first column numbers are 2, -1, -1. Then we have a column of zeros, 2, -1, -1, times the vector of variables equals to the 0 vector, right? And again, solving this one, we're going to let, when you multiply this, x sub 3, you can let it be whatever s. X sub 2 ends up being t, and x sub 1 be -s. So you get 2x1. Let me write one equation for you. This first one. First row, first column. So I get 2x1, 0, and then I get plus 2x3 equals 0. So from this, x1 equal -x3, or x1 plus x3, x sub 3 is 0. And therefore, x1 equal -x sub 3. So if x sub 3 is s, x sub 1 would be -s. So that's how I solve this. Okay, and then we have our basis vectors. So b1 is going to be -1, 0, 1, and then we have 0, 1, 0. So I pick up 2 basis vectors from this one. How does this come about? Well, remember the solution x here. X is going to look like this. It's going to be x sub 1, -s, x sub 2, t, and x sub 3 is s. Good. Now I can write this as sum of 2 column vectors. Okay, so it's going to be s times -1, 0, 1, plus t, 0, 1, 0. Right? We put these together, you get exactly this. See, -s plus 0 is -s. S times 0 is 0. T times 1 is t. They add to t, and so on. Okay, and that's how I picked up these vectors. You let S be 1, and here you let T be 1. So we pick up 2 eigenvectors for the basis here, first basis. Okay, so again, these 2 vectors form a basis for the eigenspace corresponding to lambda equal to 2. And that's what we wanted to do, remember? We want to find basis for eigenspace of A. Now, these are corresponding to lambda 2. When lambda is 1, and by the way, I want to show you something. Remember, lambda 2 had multiplicity of 2, so there are 2 eigenspaces of A. So corresponding to lambda 2, because there's multiplicity of 2, we picked up 2 eigenvectors, okay, for that one. If multiplicity, let's say, was 3, you pick up 3 eigenvectors for that. Lambda 1 has multiplicity of 1, so we're just going to get 1 basis for the eigenvector of this one. When lambda is 1, the matrix becomes 1, -1, 1, 0, -1, 0, 2, -1, -2, times the matrix of variables equal to 0, 0, 0, solution to non-homogeneous system. You do Gauss-Jordan on this, and the solution turns out to be 1, 0, 0, 0, 1, 0, and 2, -1, 0. That's doing Gauss-Jordan on A. And then from this, again, we have a row of zeros. So that means we have parametric solutions. The free variable is x sub 3 here. So I let x sub 3 be t. X sub 2, move -1 to the other side of equal sign, becomes +1. That means it's t also. And x sub 1, move 2 to the other side. X sub 1 becomes -2t. There. And put it together. Here, the vector x, factor the t out, and that's going to make it -2, 1, 1. And here is again another basis vector, another eigenvector. Okay. So, and there you have this one. Okay, so we found all of the eigen, uh, we found the bases for the eigenspace of A. And there you go. These are the basis vectors that we found. These. Okay. Again, is everybody okay with this work? Any questions on this? No, no questions. All right. Now, if no questions, then let's move on to our next section. Okay, let me change my share with you. I'm going to share the page of the book with you. And let's see, what we would like to do next is, so we talked about eigenvalues, eigenvectors. Yeah, all of these we talked about. If you have a a triangular matrix, remember a triangular matrix is a matrix that has zeros above or below the main diagonal, then your eigenvalues are simply the diagonal elements. So for a triangular matrix, and also for matrices that, there you go, see they have zeros above and zeros below. For these, the eigenvalues are going to be -1, 2, 0, -4, and 3. So something that we will do in section 2 is it's called diagonalization, where you turn these into diagonal matrices. And that is primarily why we're going into the next section, to diagonalize these matrices. Okay. Let's go to section 2, folks. Section 7.2, diagonalization. So to diagonalize a matrix, again, means to do, here's a definition. That means you can write it as a matrix in this form. Okay. Now, what do we want to diagonalize a matrix? Again, when we diagonalize, that means you have numbers on the main diagonal, okay, on the main diagonal, and off diagonals will be 0. Now, the reason this is ideal, that's why we want to do, is because it simplifies matrix powers. So if you want to raise a matrix to a power, then this makes it really easy. Okay, and let me see if he shows that to a power. No, but I'll show you when I go to my .cam here. I'll show you what I mean. So that's one reason. It simplifies matrix powers. The other one is simplifies solving differential equations. Okay, so it just makes it a lot easier. And there are other benefits of it too. So there are a lot of benefits to having a matrix that is diagonalized. Okay, so let's go through this real quick. Now, first, similar matrices here, because when we diagonalize, we create similar matrices here. And what you see here, this matrix B, which is in the form P inverse AP, it's going to be similar to matrix A. Okay, so here it says two matrices are similar when there's exists. And now, chapter 6, by the way, that section we did not cover, but that's what this is. Two matrices are similar matrices when you can find an invertible matrix P so that this equation holds. You can write B as a product of these other three matrices. So A and B are called similar. Okay, so What matrices are diagonalizable? The matrices that are similar to diagonal matrices. Okay, so this is a definition of a diagonalizable matrix. Suppose we have a square matrix A. You can turn it into a diagonalized matrix when A is similar to a diagonal matrix. And what does our diagonal matrix look like? It's going to look like this. Okay. Now, I'll show you how this works, but in his example, so suppose he has this matrix, and this matrix is diagonalizable because there is a matrix P. I'll show you how to find P here in a few minutes. This P is directly related to like eigenvectors of A. So I'll show you again. But somehow, let's say we know what this matrix P is. If you do inverse of P times A multiplied by P, look at this matrix. You see this matrix now? It has numbers on the main diagonal and 0 off diagonal. So the matrix A has been diagonalized. Isn't that cool? So it turns it from one form to another. Now this diagonalization, by the way, Symbolab does it, so we don't have to do this by hand, but it's good through just the process. And then we definitely use Symbolab to do this. Now, so I still owe you this. How do we know what P is? That's the key here. Because A is given. A is given. Our goal is to find this last matrix, P inverse AP. There, call it D, matrix D, diagonalized matrix. The big mystery right now is where does this P come from? That's it. Now, similar matrices have the same eigenvalues. Okay, so if two matrices are similar, then they have the same eigenvalues, and this is the proof of it. So in the example above, you have matrix A, and this matrix diagonalized version R, these are similar. So that means they have the same eigenvalues. And just earlier, we said if you have a triangular formation, the numbers on the main diagonal are eigenvalues. So the eigenvalues of A are 4, -2, -2. Isn't that cool? So when you diagonalize a matrix, you're actually looking at the eigenvalues. And once you have the eigenvalues, we can go to the eigenvectors. And it's like, okay, then what? Well, then we can do whatever it is we want to do, such as solving systems of differential equations. Okay. Now, and there you go. Here's just another example that it shows here. It says you find eigenvalues. There, we already did. It's easy to find eigenvalues once the matrix A has been diagonalized. The eigenvalues are 1, 2, 3. There you go. So that means this would be the characteristic polynomial. Remember lambda minus the eigenvalue, lambda minus second eigenvalue, lambda minus third. That's the characteristic polynomial. Okay. This next theorem gives us the condition for diagonalization. The condition is A is diagonalizable if and only if it has n linearly independent eigenvectors. Otherwise, it's not diagonalizable. Okay. This one, I'll show you an example how to do this. Here are the steps. Again, these steps I'll show you in an exercise, in an example, actually. We'll do it together and you'll see how this works. So let me just skip this part. We'll do our own in a few minutes. But remember, the end work result of section 7.2 is this right here. You see that? P inverse AP, that's all we want. That's a diagonalized matrix. And from this, we know the eigenvalues, and hopefully we can find the eigenvectors too. Again, this theorem, sufficient condition for diagonalization. A square matrix has n distinct eigenvalues. If it does, they are distinct. They have to be different. No multiplicity here, other than 1. And the eigenvectors are linearly independent. and A is diagonalizable. Okay. Let me go to this one. Linear transformation. Actually, let me skip that part. And, oh, cool. So we reached the exercises. Now, let me actually, I want to tell you something here that I didn't see it in this section, but this is true. So I'm going to change my share, folks, to my notepad here now. Okay, and let's do this for my notepad. All right. Um, and this, okay. So what I want to tell you about is the similarity. It's called similarity of invariance. Okay, and here's what I mean. Let me just actually write that. The similarity of invariance. Okay, and this is what similarity of invariance is, what I mean by it. So here, suppose again we have a matrix A, square matrix, right? The matrix A and the diagonalized version of it, P inverse AP. Remember, these are going to be similar matrices, right? They have the same determinants. Okay, so there you go. So that's one good thing that comes out of this. This matrix A is invertible if and only if the diagonalized version, the similar matrix to it, is invertible. So pretty much they're going to share a lot of common attributes, but one attribute is not going to be common. So let's keep going. This one, A and P inverse AP, the similar matrix, the diagonalized version of A, have, now here are the things they have. They have same rank, and I'll show you this in an example, by the way. They have the same nullity. Remember, nullity is a number of vectors in the null space for the homogeneous system, right? Nullity. And they have the same trace. And if you recall, trace of a matrix is the sum of the diagonal elements. We talked about the trace earlier in, not sure, I think it was chapter 2, maybe we talked about it. And they have the same characteristic polynomial because they're similar. This is consequence of similarity. Same characteristic polynomial. And they have the same eigenvalues as a result, right? If they have the same characteristic polynomials, that's the solution to determinant lambda I minus a. They have the same characteristic polynomial. It stands to reason they have the same eigenvalues, right? And here's the next one. If lambda is an eigenvalue of a, an eigenvalue of a, and hence the diagonalized version of it, then the eigenspace of A corresponding to lambda and the eigenspace of the similar matrix, diagonalized matrix corresponding to lambda have the same dimension. And remember, the dimension of the matrix is the number of vectors, right? Number of vectors in the basis, right? So that's what we mean by dimension. Now, here is how they are different. A and call it B, but then B is the diagonalized version, okay, of P inverse AP. They do not have the same eigenspace. Okay. So they share everything else pretty much, right? They have the same rank, same nullity, trace, characteristic polynomials, eigenvalues, same dimension, but they don't have the same eigenspace. Okay. In other words, this is what that last part means, and that's important. When we look at the solution to lambda I minus ax equal to 0, and when you look at the solution to lambda I minus P inverse AP, the diagonalized version of itself, right? Although they are similar, equal to 0, that one, these have different eigenvectors. Okay, they have different eigenvectors. Now, I'll do an example of this, and you will see for yourself how this actually plays out. Okay. So again, hopefully everybody's okay on these similarity of invariance. We're talking about invariance between A and the diagonalized version of matrix A, which is called the similar to A. Okay, that would be B. A and B are similar. Again, everyone okay so far, I hope. If not, please ask questions. So if we're good, then let's take a look at an example of what I just put for the last piece. The eigenspaces are different. So for this example, in this example, we are again in section 7.2 now. Okay, so I picked this 3 by 3 matrix. Okay, it's going to be 0, 1, 1, 0, 2, 0, negative 2, 1, 3. And for this one, the characteristic equation, that would be lambda I minus A or A minus lambda I. Remember, it doesn't matter. Your book goes lambda I minus A, so I did the same thing. And this one's going to be lambda minus 2, lambda minus 3 for the diagonal. Off diagonals of A, what are going to change? 0, negative 2, 1, 1, 1, 0. Okay, so for this one, when you, this is determinant. Again, I got to be careful with this one. See, it's not a matrix, it's the determinant of a matrix. So this one, I worked this determinant in Symbolab. The characteristic polynomial, again, turns out to be this, minus 4 equals 0. And this is the one we did earlier, actually, right? And I got the factored form using the rational zero theorem. So for this, you pick up the eigenvalues, lambda 1, lambda 2, multiplicity of 2. Okay, now I explained about multiplicity here. Let me just, for now, I'm going to write what we just found, because we found this multiplicity algebraically. In fact, we're going to call that, this is called algebraic multiplicity. Okay, that's just the terminology. Later, we talk about geometric multiplicity. So this is algebraic. It came from the characteristic polynomial. Now, plugging lambda equal 1, right, the eigen values into this matrix, into lambda I minus A. Okay, and when we do, we're going to get 1, negative 1, negative 1, 0, negative 1, 0, 2, negative 1, negative 2, right? That's this lambda I minus A. And remember, just like before, we're looking for non-trivial solution to the homogeneous system. Okay, and then when we solve this using Gauss-Jordan, what I got is the following. I get x1, x2, x3, and you can verify this. You're a pretty smart group, so this is no big deal for you. You can figure this out. And negative 2s, s, and s, and therefore, my first basis ends up being, just factor the s out, ends up being negative 2, 1, 1. Okay. Now, I just want to point out that this one, the dimension of this basis is 1 because there's one vector in the basis. And this basis, I'm going to label this as P sub 3. Okay, I'll explain that. You'll see in a few minutes. I'm doing the procedure for finding the diagonalized matrix here. Okay, so there you go. This is going to be an eigenvector corresponding to the eigenvalue. Now, you look at lambda 2. It's lambda 2. Remember, this one has multiplicity of 2, right? So I'm going to get 2 eigenvector corresponding to this one. And when you plug this in, you get 2, negative 1, negative 1, 0, 0, 0, negative 2, negative 1, negative 1. And do Gauss-Jordan on this one. Gauss-Jordan on this. And the solution ends up being x1, x2, x sub 3 equals, for this, I got negative s, t, and s. So I actually end up with 2 eigenvectors of this one, 0, 1, 0. Okay, so my second set, these are the basis vectors, is going to be negative 1, 0, 1, and 0, 1, 0. The dimension of this set, because there are 2 eigenvectors in this set, so this has dimension of 2. Label the first column vector as P1, the second one as P2. Okay, so therefore, the eigenspace, which is made up of the total basis vectors, right? The total basis vectors that you see here has 3 eigenvectors. So this is the sum of these two becomes the eigenspace of that matrix A. Okay, so these are my eigenspace vectors in the eigenspace. Now, let's take a look at the diagonalized version. I'm doing the procedure that's in the book. I said we'll do it ourselves. So here's now, we're looking for that P and then do P inverse AP. So what is this P? P is going to be made up of P1, P2, P3. These are the basis vectors, right? And that's why I labeled them P1, P2, P3. These come once, these are the eigenvectors, actually. That's all they are. So you can write it in this form. P1 is, this one is corresponding to lambda equal to 2, right? So this is going to be negative 1, 0, 1. This is a matrix of P1, P2, P3. It's going to be a 3 by 3 matrix. The second vector, eigenvector in the basis for the eigenvalue is going to be 0, 1, 0. The second vector, eigenvector. And corresponding to lambda 1, I have this vector, -2, 1, 1. Okay. So hopefully everyone's good still. Now, so this is matrix P. There you go. That's P. This is how you form that matrix P. Remember, our goal is to find P inverse AP. That's what we want to do. Now, we can find the inverse of this matrix, right? The inverse, I found it from Symbol Lab. The inverse of this matrix ends up being 1, 1, -1, 0, 1, 0, 2, 1, -1. Okay, and again, I use Symbol Lab for that. Now, let's call matrix B the similar matrix to A. It's P inverse AP. So this is going to be P inverse is this matrix. 1, 1, -1, 0, 1, 0, 2, 1, -1 times matrix A, the original matrix. Let's see, matrix A, I'll show you, is this matrix, the matrix we started with. Okay, so that's gonna, what is that gonna look like? That's gonna be 0, 0, 2, 1, 2, 1, and 1, 0, 3. Okay, so that's matrix A, and P, of course, is the matrix of eigenvectors. So it's going to be -1, 0, 1, 0, 1, 0, -2, 1, 1. And there you go. So I have to multiply these three matrices together. And again, I did. I used Symbol Lab to do this. And check out what I got. I got 2, 2, 1, 0, 0, 0, 0, 0, 0. Like magic. And there you go. So matrix A is now diagonalized. Now, one thing that you can note here right away. Remember the first column of this basis eigenvector, this set, was corresponding to lambda 2. Lambda 2 gave me 2 eigenvectors. And those are the eigenvectors. You see that? And this is lambda 1. Now, the way I wrote it was P1, P2, P3. So the elements 2, 2, 1 here, these could take on different shape. I could have 1, 2, 2, 2, 1, 2 like that, depending on how you order the P1, P2, P3. But order doesn't matter. Order doesn't matter here. So we can order P1, P2, 3 in any order. Okay, but what's interesting is that, let me just write out what I just observed. The eigenvalues is in same, we're talking about eigenvalues here, 2, 2, 1, in same order of lambdas in P, right? Again, I have P1, P2, P3, P1, P2, P3. So that's going to be corresponding to lambda 2, 2, 1. And there you have it. Isn't that cool? Now, let's do something real quick. This, let's see. This actually, yeah, let's do this. I was gonna say let's take a break, but let's go through and do this one, and then we'll take a break. I think I could manage to do this in 10 minutes. Okay. Now, what we want to do next is let's find, this is a continuation of this exercise. Let's find the eigenspace of B. Remember, B was the diagonalized matrix, right? And this is what B was, the one we just observed. It's 2, 0, 0, 0, 2, 0, and 0, 0, 1. That's what our B was. We want to find the eigenspace of this one. And this is indeed, again, P inverse AP. I want to find the eigenspace of B. Remember, I mentioned in a note that they have all those invariant properties. Everything is the same except the eigenspace. So let's try to find eigenspace of B. For this, we do lambda I minus B. So that means lambda minus 2, lambda minus 2, lambda minus 1, 0, 0, 0, 0, 0, 0. This determinant is easy to do, right? You multiply the diagonals because it's a triangular matrix. So the characteristic polynomial is going to be exactly the same as before. No surprise. The eigenvalues would be the same, right? Because that's what we said. 2 and the multiplicity equals 2. Okay, so that we confirmed it, in fact. They have the same characteristic polynomial, same eigenvalues. Now let's go lambda equal 1. That's when you put 1, 1, 1 here. So when we do, look what we're going to get. We're going to get negative 1, 0, 0, 0, negative 1, 0, and then a row of zeros, right? That's 1 minus 1, 0. Now, this one, you do Gauss-Jordan, you're just going to lose the negatives, right? So you get something like this. Now, from this, there you go, if you will, Gauss-Jordan, just multiply top, bottom row by negative 1. So from this, we get x1 is 0, x2 is 0, and x sub 3 is t. Therefore, the matrix X is going to be 0, 0, t. Factor out the t, 0, 0, 1. And here we have a basis vector. This is our first eigenvector for the eigenvalue. So this one has dimension of 1, the number of vectors in the basis. Okay. Now, corresponding to lambda equal 2, do the same thing. Put 2 here, 2 here, 2 here. You get 0, 0, 1, right? So the matrix is actually easy to work with. 0, 0, 0, 0, 1. True. And from this, we get x3. Remember, we solved this homogeneous system. So there's 0 on the other side of these. x3 is 0. x1 and x2 are free variables. I'm going to let x2 be t, x1 be s. The vector here, the eigenvector, therefore, is going to be st0. That's x1, x2, x3. Factor s, write it as a column vector plus t, the other free variable, column vector 0, 1, 0. Now we have eigenvectors for this basis, right? B2, that's going to be 1, 0, 0, 0, 1, 0. This set has dimension 2. And of course, you add 1 plus 2, you get 3. Remember, the eigenspace has total basis vectors, which is in B1 and B2 combined in these two. 1 here, 2 here. So the eigenspace has 3. Now, let me put these side by side for you. Earlier, we said the eigenspace of A were these. It turned out to be negative 2, 1, 1, and negative 1, 0, 1, and 0, 1, 0. The eigenspace of B actually ended up being the vectors that you're observing, ends up being 1, 0, 0, that's this one, 0, 1, 0. It looks like identity matrix, doesn't it? And this one, 0, 0, 1. There you have it. And you see that they are different. See, these vectors are different. They're not exactly the same. And that's what I was trying to say in the note. Now, the things they have that are equal, if you look at the trace, for example, trace of matrix A, trace of A, the sum of the diagonal elements of A would be, let me see, let me put A here. This was matrix, which one was it? There you go. It was this one. Matrix A. Trace of A is 0 plus 2 plus 3. So I'm referring to this matrix, folks, for the next few items. The trace of it is 5. What's trace of matrix B, the diagonalized matrix? 2 plus 2 plus 1. That's 5. So trace of the diagonalized, the similar matrix is 5. And let's look at again, of course, we verified that already. The eigenvalues were exactly the same. 1, 2, 2. This one. Lambda was 1, 2, 2 also. What's the rank? The rank of this, the matrix, the rank of this would be 3. That's the rank of actually matrix A was 3. It was 4 rank. So is matrix B. And the rank of this matrix is 3. Number of non-zero rows, independent rows. The rank is 3. The nullity here, let's put the nullity. The nullity is the number, it's going to be the number of columns minus rank of A. Okay, now remember, x1, x2, x3, these are equal to 0. So the number of columns, our matrix look like this. 1, 1, 1, 0, 0, 0, 0, 0, 0, like that. So number of columns in the nullity is going to be 3 minus rank 3. The nullity is 0. Okay, this is for matrix A. The nullity of B, the same thing, because you have I3. See this? 1, 1, 1, 0 elsewhere. So it's going to be exactly the same. They have the same nullity. Okay. Nullity is 0. So what does that mean? That means the null space is just the origin. Okay. And it tells you how many free variables there are when solving the system, pretty much. Okay. So there you have it, and it's 7:36. So I can now probably stop here, and we can actually take our break. So let me do this, folks. I'm going to stop the recording here real quick. Okay. So now what I want to do is I'm going to go to Symbol Lab. So let me change my share here to Symbol Lab. And we'll see how this gets done in Symbol Lab. So you should have now, you should be able to see Symbol Lab on my desktop. Okay. So I'm going to input, here's the, by the way, the tag that will do this, diagonalize. There you go, diagonalize. And we're going to stay with the problem we did before the break, which is a 3x3. And the numbers for matrix A were 0, 0, -2. And then we had 1, 2, 1, and then 1, 0, 3. Okay, so those were the elements of that matrix. And we're just going to hit diagonalize and see what happens here. Go, and there you go. The process is done. Now, a lot of these, what you see in the few steps that we're about to see, a lot of this you actually will recognize. So for example, here is matrix P. Okay, now matrix P, the matrix that we had was the first column of our matrix P before the break that I did in my notes. The first column was -1, 0, 1, which is the third column here. The second column is exactly the same as our second column. And the first column of this matrix P is actually our third column. Okay, it's just, remember, the order of P's. The P's were the eigenvectors corresponding to the eigenvalues, right? So the order of these don't matter. So that's how this one is done. And then this is the diagonal, right? The diagonal elements, the diagonal as a matrix is 1, 2, 2. Ours was 2, 2, 1. It was 2, first row, first column, 2, second row, second, and it was actually 1. So it seems like the order here that you see matches the order that Symbolab has done. Okay, in other words, corresponding to eigenvalue of 1, the eigenvector we found was negative 2, 1, 1, and there you go. So Symbolab is doing lambda 1, eigenvector for lambda 1, so D is going to have lambda 1 here. And then the second column again corresponds to lambda 2, and that's why this is, and this one, those are the same as the ones we got. Okay, now the inverse, of course, is going to be slightly different, but nonetheless, the inverse, ours was 1, 1, negative 1. This one is negative 1, 1, 1. Our second column was 0, 1, 0. This one is 0, 1, 0 also. And our last column was 2, 1, negative 1. This one is negative 1, 1, 2. Okay, so there's clearly, because the columns here are different, the inverse will look different. And now if you look at the steps here, remember D is what I had in my notes as B as in boy. That's D. And these are the steps. So the eigenvalues, lambda 1, 2 with multiplicity of 2. That's exactly what we found. The these are the eigenvalues for matrix A. That's matrix A. The diagonal matrix, again, it's 1, 2, 2. Ours was 2, 2, 1. The eigenvectors corresponding for this, these are the eigenvectors. We had exactly the same, right? We had negative 2, 1, 1. And then we had exactly these two. So we're getting a lot of this information that we already got. Here's matrix P and P inverse. And this is the similar matrix PDP inverse. There you go. That's what this one is. No, it actually solves it. Sorry, PDP inverse. When you multiply this PDP inverse, remember we're going to get matrix P inverse. Oh, this is now the second part. The second part that we found, the diagonalized matrix. That's this one. This one, D. That's our B in my example. Okay, before the break, we labeled that as B, and that's what that is. Okay. So just want to show you again, you can do this in Symbolab, and it just does all of that stuff, but much faster and easier. Now, we're done with section 7.2. Let's actually go to section now 7.4. Okay, 7.4, because that's what we're doing. Let me go back to the page of the book. And this time, I'm going to change my share to the page of the book, share. Okay, so we've done an example of diagonalization here. Let's go to, actually go to section 4 now. In section 4, we're going to look at section 3 is orthogonal diagonalization, so you can read that on your own if you're interested. I just don't have time for everything, so just going to go to the applications now. The applications of eigenvalues and eigenvectors. Now, even in applications, there are different applications. The example you see here, population growth, I'm going to skip that one. The other application is this one. The one that I want to look at is systems of linear differential equations. So this, it says calculus, but it's really differential equations. But anyway, so what we want to do is we actually want to solve this system. Okay, Now, the system that you see here is called a first order linear differential equation. It's called first order because you're working with first derivatives. Okay, y sub 1 prime, y sub 2 prime, y sub n prime. Together, these form a system. Now, the general form of this, you see a sub 1, 1, y sub 1, and so on. So this is nonetheless, that's our first order system. Now, here the matrix Y is matrix of solutions. Y is the solution to the system. Y1, Y2, dot, 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 Y sub n, and these are the derivatives that go with this. Remember, to solve a differential equation means find the Y values here. Okay. Now, so here's an example, for instance, y prime 1 equal 4y1, y prime 2 negative y2, y prime 3 2 y3. It says solve the system of differential equations. Now it says from calculus, you know the solution is given by that. Well, we'll take it for face value. Okay, so suppose these are the solutions. Then here's a solution to the system. Remember, the solution is actually going to be functions of y1, y2, and y3. Okay. And this is the matrix form of the system of differential equations here. The form is y prime equals ay. So here's y prime. A is this matrix 4, negative 1, 2, which you can kind of see they come from up here. The coefficient on y1, 4. Coefficient on y2, negative 1. Coefficient on y3 is 2. So that's what A is. Okay. Now, let's see how we're going to do this. We'll do our own example in just a moment. Quadratic forms, that's another form here. So again, in solving systems of differential equation, we're primarily interested in linearly independent solutions, okay, of the homogeneous system. That's what we're interested in. Okay, and let's see and here's another example, rotation of axes. So again, there are so many different examples here. Let me see if, there you go. We're going to skip these. Rotation of a conic. This is application to the third semester calculus. I'm going to skip these, and we're going to stay with the differential equations, okay? And there you go. So we're going to the exercises. Now, in the exercises, if I remember correctly, I've assigned these numbers like 17 through 28, not all of them, but I know you're doing like number 18, you're doing number 24. So the ones like these are the ones that are focuses. You're doing 24, and I think that's about it. On the applications, you're doing just 18, 24, and I think 20 or 22. But let me actually go to my notepad and tell you what's going on here. So I'm going to change my share and I'm going to go to my notepad. Okay. So let us do this now. Okay. So for this one, we're going to start with this example. Okay. In our example, this is section 7.4. Okay. In this example, I'm going to let y1, okay, y1 be this the solution to a differential equation. And let's say this is what y1 turns out to be, and y2 ends up being 3, 5, e2, 6t. However, I got these. So suppose these are solutions of a homogeneous first order system. Okay, so what we want to do is this. These are the solutions. How I got this, don't worry about it. But suppose these are two solutions, and we want to answer this question. We want to know whether these solutions are independent. So here's the question. Are y11 and y12 independent? So do we have independent solutions? Because if they're not independent, that means, well, there are redundancies here. We don't have distinct solution. These, if they're redundant, then I can write them as one instead of two. Now, one thing we did earlier, and this goes back to some time ago, is to determine whether a set of solutions of a homogeneous system of differential equation is linearly independent. We said we need to find a Wronskian. This was, let me just say, from section 4.8. I believe that's when that was, from section 4.8. The solutions are independent. I'm just going to say these are independent if and only if the Wronskian is not zero. Okay, and the Wronskian itself was the determinant of a matrix. So for this example, the Wronskian for y1, y2, that's the determinant of e to negative 2t, 1 times e to negative 2t, and negative e to negative 2t. That's the first, that's y1. y2 would be the second column. Now, and what y2 is going to be 3e to 6t and 5e to 6t. So there you go. That's going to be the Wronskian, the determinant of that 2 by 2 matrix. And the 2 by 2, remember the determinant, you multiply diagonals minus product of off diagonals. So you get 5 e to negative 2t times e to 6t minus the off diagonals, but then this is negative also. So we're going to get 3e to 6t times negative e to negative 2t. Now, multiplying two exponents with a common base, we're going to add the exponents. So I get 5e to 4t minus negative is positive, 3 e to 6t, e to negative 2t, those combine to e to 4t. And now we have a pair of like terms. So this is going to be 8e to 4t. And e to any power, t, is going to be something that's not zero, right? Because remember, e to t, that function is never zero. There you go. Remember the graph of e to t looks like this. So e to t is never zero, the exponential function. Therefore, the Wronskian is not zero. If the Wronskian, the determinant of that 2 by 2 is not zero, therefore we can say y1 and y2 are linearly independent. Okay, and these solutions become what they call fundamental solution of some system of differential equations. So we got the fundamental solutions. Okay, now this part now, the general solution to the homogeneous system. And that's all we're looking at in this section, folks. Homogeneous system of differential equations. The general solution ends up being like this. It's going to be y equal, and we're talking about the homogeneous system that it was in the beginning of the section. Okay, y1 e2 lambda 1t plus plus it's going to be cn yn e2 lambda sub nt. That's going to be the general solution. Here, by the way, the lambdas are distinct eigenvalues, just like before. The lambdas are distinct eigenvalues. That's why, again, eigenvalues are so important because they end up they help us solve these systems of differential equations. So these are distinct eigenvalues, and they're real, by the way, distinct, real. Eigenvalues could be complex, by the way, depending on how the characteristic equation turns out to be. But we're only looking at real ones. So these are, again, distinct real eigenvalues of, again, the coefficient matrix, right? A, matrix A, coefficient matrix A of this homogeneous system. Where is A? A is, there you go. Remember the homogeneous system, y prime equal AY. That was in the beginning of the section. All right, and this is our general solution. So we have our solution now. Again, however this is done, the book said from calculus, but there you have it. In the differential equation class, they derive this. Now, let's take a look at an example here. Okay, in this example, we want to solve the system of differential equations. Suppose y prime 1 is 2y1 plus 3y2. Now, this is like your homework problem, folks. So there you go. Hopefully, this will help you solve your homework problems. 2y1 plus y2. So again, I have a system of equations here. So what is A? Again, this is in the form y prime equal AY. A are the coefficients here. Coefficients on y's. So A is going to be 2, 3, 2, 1. Okay, and this will have distinct eigenvalues. So what do I need to do? I need to find eigenvalues. Why? Because that's what the solution is calling for. These are eigenvalues. So I need to find the eigenvalues and possibly and eigenvectors. Okay, and eigenvectors of A, the matrix of coefficients. So we're going to do our routine A minus lambda I. And this is going to be 2 minus lambda, 1 minus lambda, 3, and 2. The determinant of a 2 by 2 matrix, again, the 2 by 2 is easy. We don't need symbol lab, so you do diagonal minus the off diagonals. We do that, the 2 binomials, and then minus 3 times 2. All of that should be lambda squared negative 3 lambda minus 4, which factors into lambda plus 1 times lambda minus 4. Set it equal to 0, and lambda 1 ends up being negative 1 or 4. So those are the two eigenvalues, correct? Now, we want to find the eigenvectors. For eigenvectors, we need to look at the solution to the homogeneous system, A minus lambda I, y equals 0. That will give us the eigenvectors. A minus lambda I, so A is, remember, A is 2, 3, 2, 1. A is right up here. And then minus lambda I, that's when you put the lambdas, negative 1 and 4, in the diagonal of the identity matrix order 2, second order identity matrix. There you go. So that's the A minus lambda I multiplied by vector of unknowns, y1, y2, and that should equal to a 2 by 1 0 matrix or vector, a column vector. So we need to solve this one. Now from this, we get 2 minus minus 1, that's 3. So you multiply 3 times y1, and then you go 3 minus 0 is 3, 3 times y2. So I'm going to get the system, 3y1 plus 3y2 equals 0. The second equation, likewise, will give you what? 2y1 plus 2y2 equals 0. And from this, you can see, for example, the first equation, divide everything by 3, second, divide everything by 2. However you do it, from this, we get y1 equals negative y2. So y2 becomes our free variable. We're going to let y2 be t, our free variable, and therefore y1 is going to be negative of t. And with this, we have the solution vector, right? Y would be negative tt, to this 2 by 2 matrix, factor a t out, and there you go. This would be the eigenvector, right? That is eigenvector corresponding to a minus lambda I. Okay. And by the way, lambda here I used was this one, -1. Sorry, I didn't write it. This is lambda 1 equals -1. That's how you get -1, -1, -1 for this one. Okay. Now let's do the eigenvalue lambda 2 equals 4. Let's try that one. So corresponding to lambda 2 equals 4. We're going to try this one. Lambda 2 equals 4. What is this going to look like? Well, that means you're going to do A, 2, 3, 2, 1, -4, lambda 2 is 4, minus lambda I, so it's going to be 4, 0, 0, 4. Remember, I is the identity matrix. And then now multiply by y1, y2 equal to 0, 0. And then set up a system for this one. The matrix 2 minus 4, so it's going to be -2. Then we have 3, 2, -3, y1, y2, and then 0, 0. So from this, we can get, again, a system of equation, -2y1 plus 3y2 equals 0. And then 2y1 -3y2 equals 0. And then we can solve either one of these. Let's say from the second one, we get y1 equals 3/2 y2. So we're going to let y2 be our free variable. Therefore, y2 is going to be 3/2 t, right? Free variable y2 is t, so that's y1 would be 3/2 y2, and y2 itself was t. The order of the elements in this column vector is y1, y2, right up here, y1, y2. Okay, and then I can factor the half t, and there you go. So this would be the eigenvector again. Now, if you noted, A was 2 by 2, right? So we expect two linearly independent solutions, and you can see the dimension of this eigenspace. I have a vector in this one, and I had a vector in the previous one, right? True. We have these vectors. We have a vector here, and we have a vector here. So the dimension is 2. Total dimension of the eigenspace of A is 2. And that means we have two linearly independent solutions. Okay, now we can actually write the solution. The solution is C1, Y1, E2 lambda 1 T plus C2, Y2, E2 lambda 2 T. That means C1 is like, think of it as the constant of integration, right? If we have initial value problem, that means they give us an initial value for y1, y2, like at 0, y is 1, at 2, y2 is 4, whatever. That will help us determine these constants. But right now, we're going to leave them alone. Remember, the eigenvalue was -1. The first one I had was -1, so this is corresponding to -1. That's first one, plus C2, and Y2, or Y2 is this one, 3, 2. Any multiple of that, by the way, works. E2, 4T. And there you go. This will give you a family of solutions. A family of solutions. There you go. Just like um, indefinite integrals in Calc 1, remember? If you have definite integrals, that means you have limits of integration. You don't need constant of integration. And we get a specific antiderivatives. If the integral was indefinite, if I'm thinking Calc 1, folks, then you have a family of antiderivative. You have a constant of integration. So that's what these are. They act as constant of integrations. Okay, and there you go. We just solved the differential equation for that exercise. Okay, now what if we have, let's say, repeated eigenvalues? Okay, so we're going to look at another example for this one if we have repeated eigenvalues. For the repeated case, so let's say we want to solve this system of differential equation where y prime is equal to ay. And this time, let's say where A is going to be this matrix of the coefficients on y's, 1, -2, 2, or -2, 1, -2, and then 2, -2, 1. So when you do the exercises, folks, you need to come up with these matrices, the A matrix. So we need to find a characteristic equation first. That would be A minus lambda I. Because remember, we need eigenvalues, because what goes here are the eigenvalues. And the y ones, these are the eigenvectors, right? The eigenvectors that go with those eigenvalues. Okay, A minus lambda I here. So we're going to go to the determinant of 1 minus lambda, 1 minus lambda, and 1 minus lambda, -2, 2, -2, -2, 2, -2. There you go, that determinant. Now this determinant, you can try it, but you can see here the similarities that you see in the matrix. But you can run it through Symbolab and see for yourself. That determinant is 0. Okay, the determinant. Actually, let me just say this. I'm sorry. I'm going to set it equal to 0. In a moment, I'm going to do the determinant for you. When the determinant doesn't turn out to be 0, folks. Sorry, I didn't mean to confuse you. But remember, we get the characteristic equation, we set it equal to 0. So again, the determinant isn't 0, but we set it equal to 0 to find the eigenvalues. Now, the actual characteristic polynomial in factored form ends up being this. Now we set it equal to 0. That's what I meant. And from this, we get lambda 1 equal lambda 2 equals -1, and lambda 3 is 5. So we do have repeated eigenvalues. Okay, so let's try lambda 1 equals -1, just like we did earlier. And now we're going to solve this system, A minus lambda I equals 0. Okay, the homogeneous system, in other words. What does A minus lambda I looks like? Remember, this is A, and lambda I is when you put lambda -1 here, here, and here. Okay, so when you do that, this ends up being 2, -2, 2, -2, 2, -2, and 2, -2, and 2. And again, you do Gauss-Jordan on this. When you do Gauss-Jordan, what happens is you get the first row becomes 1, -1, 1, 0. And then we have 2 rows of zeros for this one when we do Gauss-Jordan. Okay, now, well, from this, remember, these are the coefficient on y1, y2, y3. y1, y2, and y3. So our free variable is going to be y3 and y2, correct? So I'm going to let y3 be t. y2, the other free variable, let it be s. And then y1 is therefore, you move y2 to the other side, becomes positive. Y3 to the other side becomes negative. So it's y2, which is s minus y3, s minus t. That's what y1 is. Okay, so y, therefore, that matrix is going to be y1, y2, which is s, and y3, which is t. Now, for this one, because this is repeated, We've seen an example like this before earlier in the evening. So I'm going to let S1 be 1 and T be 0. Not both of them 0, by the way. One of them is okay. So when I do that, the first solution, when T is 0, you get 0 here, you get 1, 1. So that solution is going to be 1, 1, 0. Okay. And then another time, again, this is just me. You could choose any value you want. There are infinitely many eigenvectors. So once you have the basis one, then all the other ones are multiples of it. That's what this means here. So this is going to be y2. I'm going to let s1 be 1, t1 be 1. If you want, you can let s be 0, t be 1. That's just me. Plug in these numbers, 1, 1 in here. So you get 0. And then s is 1, t is 1. So you get 1, 1. And there you have that one. This is going to be the solution to y2, right? So neither of these eigenvector is going to be a constant multiple of the other, okay? So in other words, we have found linearly independent solutions here. And let's do this one. We're going to say that one solution is 1, 1, 0, e to negative t. And the other one, y2, is going to be 0, 1, 1, e to negative t. This is one solution. That is corresponding to the first repeated characteristic, this one, the eigenvalues, when we have repeated. So there you go. And then we still have another solution. Let's take a look at our next solution. The next solution is when the eigenvalue, this one, lambda 3 is 5. Let's try that one. So for this one, now we have a minus lambda I, lambda is 5. And then we solve the homogeneous system. The a minus 5i, that ends up being negative 4, negative 2, and 2. The second column, negative 2, negative 4, negative 2, 2, negative 2, negative 4. And of course, you have this column of zeros. I'm just writing a minus 5i. Do Gauss-Jordan on this one. When you do Gauss-Jordan, what we're going to get is, I did symbol lab again, folks. That's how I'm getting these quickly and easier. Negative 1, 1, 0. That's what it looks like. And now we can write the solution. Again, we have a row of zeros, and the free variable is going to be y3. These are the coefficients on y1, y2, y3. Therefore, from the first equation, we get y1 equal y3. But then from the second equation, we're going to let y3 be our free variable. So y2 is equal to negative y3, and let y3 be the free variable t. Therefore, the other solution here is y1, which is y3, means t. Negative y3, that's y2, that means negative t, and t. Factor out the t, and then we have this column vector 1, negative 1, 1, right? And there you go. Now we have our general solution to the differential equation, and our general solution is going to be, again, C1, Y1, E2 lambda 1t plus C2, Y2, E2 lambda 2t plus C3, Y3, E2 lambda 3t. Okay. So let's write this. Therefore, our solution to the whole thing is C1, 1, 1, 0, e to negative t. Remember, that was from earlier, right? A few minutes ago. There, this one. Remember, I have two solutions already. So I'm just writing the whole general solution for all characteristic, or I'm sorry, for all eigenvalues. So that's this one. And then the other one from previous page, I'm copying, I get 0, 1, 1, and then e to negative t. And finally, this, the one that we just found, C3, and then of course 1, negative 1, 1. That's the eigenvector that goes with that eigenvalue, E2 eigenvalue times t. And isn't that cool, folks? There you go. That is the solution to that differential equation. Okay. Now, if you noted, by the way, we're almost done, folks. We're done here almost. I'm going to go back to matrix A. That we did this. Okay. This was matrix A. Let me write our matrix. Just want to finish this on a note here for you. This was our matrix A for this exercise. Remember, it was symmetric. Negative 2, 2, negative 2, right? So this is a symmetric matrix. That's what we started with. So because A was symmetric, for symmetric matrices with real entries, we can always find n linearly independent eigenvectors. Okay, so as long as this is symmetric, so this will always, in other words, have a solution. We can always find, let me finish it on this. We can always find, if A is symmetric, we can always find n linearly, and n was 3 here. Remember, it's a square matrix of order 3. So we can find n linearly independent eigenvectors. And remember, each eigenvector appears here, 1, 2, 3. So that means these are the y1, y2, ... These are the eigenvectors that we found. Here, the y's are eigenvectors. These y's are eigenvectors. And there you have it, ladies and gentlemen. So we are done with what we were supposed to do. So let me actually stop the recording here because we are done with the lecture.